So we are not alone. Today we are going to talk about flexibility and 24/7. Our first speaker is Martin Kerin, a Technology Enablement Manager for Future Operations at EirGrid, the Irish TSO. And of course, Dr. Iegor Riepin, research scientist at the Technical University of Berlin, TU Berlin, who is going to introduce us to the world of 24/7 carbon-free energy. The two presentations will follow one after the other with a short Q&A for clarification questions for Martin. And now a short introduction for those who do not know RGI or are wondering why we are dealing with these topics. Because RGI is a collaboration of not only electricity transmission system operators, but also of environmental and climate NGOs. And this is why we would like to strengthen the knowledge to create additional knowledge and capacities for NGOs to be well equipped for the energy transition. The energy transition has more and more technical aspects that one should be aware of and deal with. And this is why this series is actually dealing with flexibility in the 24/7. How we organize our work, we have three dimensions which do not work in silos, but rather we create synergies between each dimension, the energy and system, or otherwise the technical dimension of RGI that deals with energy system planning and designing a decarbonized energy system, energy and nature, which explores how to develop the grid in line with nature protection and restoration. And of course, then the societal dimension that explores how to include, how to engage citizens, civil society in a participatory manner in energy system planning, but also all policy making processes for the energy transition. Without further ado, I would like to give the floor to Martin to introduce us to flexibility, what is flexibility, why we need it, and how we can actually unlock its potential towards decarbonization. Martin, the floor is yours. Feel free to share your screen.
Thank you very much. Alex, I'll just share my screen now. Okay, is that appearing okay now? Okay, fantastic. Thank you very much, folks, for your time this morning. My name is Martin Kerin, Technology Enablement Manager at EirGrid, the TSO for Ireland. And today I'm going to bring you through a presentation on an introduction to flexibility in a renewables-based energy system. So what do we mean by that? So it's looking at what is flexibility, why do we need flexibility, how can flexibility be developed, and especially using some examples from our own power system in Ireland and Northern Ireland, and then having some summary conclusions. So what is flexibility? It's a term that's used a lot, and unfortunately there is no one single definition. It does kind of mean different things depending on who is using the term. So depending on who's using it, from policymakers, system operators, industry, academia, or civil society, what is it being used for? So what is the intention of the flexibility? Is it for balancing supply and demand of electricity? Is it for managing the flows on the electricity networks? Or is it for managing system security? And then how is the flexibility being provided? So is it through technologies or different ways of working? So it can be a bit confusing using this term, but to try and be helpful, it's useful to maybe think of it in an abstract way, where flexibility reflects resources which have certain characteristics which are useful in the context of operating conditions, which are being used to manage different system needs. So flexibility is helping to meet needs on the power system and are useful to doing that in the different operating conditions on the system. So in the next few slides, I have a number of keywords which we can use to try and explore this in a bit more detail, what exactly is meant by flexibility. So what do we mean by system needs? So there's kind of two main sides of this that are often used when talking about flexibility. One is simply around the balance of supply and demand of electricity, and that can be at system-wide level or a local level. So it's being able to turn up and down, so modify your generation or consumption levels to maintain energy supply and demand balance. And depending on the granularity, if it's a system-wide problem or if it's a local problem, it can be used to manage congestion on the power network by managing the network flows at a more local level, or it can look at things in a more system-wide approach. Especially in terms of system-wide approaches, when we're talking about supply and demand balance, it's often in the context of what's called net demand. And so this is demand where people are consuming electricity, but some of that is already being met by variable generation like renewables or low carbon sources. So what is the demand that's left to be met after that? And that's what is often thought about in terms of having flexibility to be able to meet the rest of that supply demand balance that isn't being met by renewables. So then the other side of things are more kind of technical aspects of the power system, where it's looking at different aspects of system stability. So these can include aspects trying to maintain security in terms of frequency stability and voltage stability. So many people will be familiar with these terms, some people may not be. So I have a brief explanation down the bottom of frequency and voltage, but kind of a simple way of thinking of them. Frequency is reflecting the fact we have an alternating current power system. That means that the current changes directions multiple times a second. In Europe, that's 50 times per second or 50 hertz. And it reflects the energy balance. So when the energy demand and supply is in balance, then it should stay around that nominal 50 hertz. When there's more energy demand than supply, the frequency will go lower. And when there's more supply than demand, the frequency goes higher. But it's important to maintain the frequency around that nominal value of 50 hertz, because all electrical equipment is designed to work at that frequency. So if the frequency deviates from that very much, it could damage the equipment. So it's important to maintain that frequency. And voltage is kind of simply, you can think of it like the pressure on the system to keep the flow going. So it's kind of like in a water network, the pressure to keep the flow going. So that's what voltage is like. So then there are a number of system needs to maintain stability of these two very important metrics for the power system. Reserves, which are maintaining frequency stability. So it's about being able to increase or decrease the power that's being provided or consumed in a fast enough way to stop frequency from changing and to restore frequency back to 50 hertz after a disturbance, like if there's a trip on the power system. Inertia also is maintaining power frequency stability. And this is kind of, you can think of it like the weight of a power system, where there is literally spinning masses from all the heavy motors from generators and people consuming power. They're spinning at frequencies which are in sync with the power system frequency. And so that physical momentum makes them slow to change their rate of spinning. And therefore that affects how fast the frequency will change when there's a disturbance on the system. So that's important to keep the frequency stable. And then reactive power is used to maintain the voltage stability. So you can think of reactive power in a simple way as the power that's used by the grid equipment to actually make the power flow on the electricity grid. So it's not the power that we end up consuming at the end of the grid, is the power that ends up making the grid be able to keep the flow going. So that's obviously important to keep the voltage stable, like keeping the pressure stable on a grid. So that's around the system needs that we need to meet with flexibility. Then what are driving some of the needs for flexibility? Some of the features, especially around renewable-based power systems, are variability and uncertainty. So I've got a simple graph at the top here, where you can see megawatt power over time, where it's changing over the course of the time. And that's kind of showing the variability. If you think of the likes of wind or solar, the amount that they'll be providing at different times will be different. And that variability is based off of different weather patterns, which change over time and are not consistent. So this is an important feature to be able to address when you're bringing in flexibility to manage high renewable power systems. But there's also levels of uncertainty, because while there is that variability over time, you are trying to forecast what that level of renewable power will be, but your forecasts could have errors in them in shorter timescales. So you might be off by 5–10%. In medium-term timescales, you're also worried about power stations tripping off the system and being forced out. So there's uncertainty there about the availability of resources. And there's also, in longer term timescales, security of supply and capacity adequacy concerns. So making sure you have enough generation to meet the peak demand whenever that might end up being during the course of a year. So these are important characteristics we try to consider when bringing on flexibility to manage the power system. And lastly, then there are two other aspects when thinking about flexibility around external signals or requests. So how do we actually use the flexibility? So if you think of different triggers to be able to make available or utilize flexible resources. These can be explicit, where it comes from an actual system operator. For example, if there is a product which is being procured and on the person who's successful in providing that product is signaled by the system operator to do something and provide that flexibility. Or the signal could be implicit, where it comes from information that's generally available. And the example I like to use there is where there could be customers, even including ourselves with smart meters. If we have information on market prices or tariff prices from our energy supplier, if they're different in different periods, we can take that information and decide to change our consumption. And that's also providing an aspect of flexibility. We're not being told to do it, but we have information available to us to act on. And lastly, then, in terms of timescales, there's different needs for flexibility at different timescales. So as I mentioned, there's around that inertia requirement, which is really instantaneous, around keep that almost to the millisecond level of being able to respond to system events and keeping things stable. Things can go up into, if we look at the graph down the bottom, we have these reserves, which also kick in a number of seconds to try and keep the frequency stable. And there's different levels of requirement over 5 to 90 seconds, 90 seconds to 20 minutes, up to 12 hours. Then you can get requirements that go into daily and weekly patterns when you think around the weather in terms of the sun and the wind. There's also seasonal patterns, again, when you think of weather in terms of the temperature, which you need to try and manage. And there's all the way up to multi-year changes, then how things are changing over the course of a number of years. And then some solutions in terms of flexibility could meet multiple of these different timeframes, so shorter and longer timeframes, while others might be optimized to focus on shorter or longer timeframe needs. So they're really an exploration of the keywords that come up when you're thinking about flexibility. And so what I'll do now is go into a bit more on why we need that flexibility. And really, to me, there's three main drivers at the moment. One is around decreased ability to meet system needs in a flexible way. Then there's also an increased requirement on meeting system needs flexibly. And then we're trying to also maximize the use of the network and renewable energy sources. So starting off with the first one around the decreased ability to meet needs. So there's this obviously a move towards a decarbonized power system, but many of the sources of low or zero carbon energy are not inherently able to meet system needs in a flexible way. So the term that's often used for most of these resources are inverter-based resources. So these are resources which are connected to the power system with a conversion from direct current to alternating current. And that's the case for the likes of wind farms, solar generation, batteries, interconnectors, etc. And what this means is they cannot be synchronized with the AC grid, and so they aren't able to support the system with the automatic synchronized responses that other technologies can. And these resources, the likes of wind and solar and batteries, are replacing conventional fossil fuel generators, which historically have been synchronized with the AC power system and therefore could meet the system needs in that flexible, synchronized, automatic way. So therefore, other flexible resources are needed to replace the flexibility which is being lost from the conventional fossil fuel generators. At the same time, not only do these inverter-based resources, are they less able to meet power system needs in a flexible way, they also cause additional flexibility needs on the power system. They cause additional insecurity and instability, which needs to be managed. So, for example, their reactions to disturbances on the system, like if a generator trips, that can cause make changes in the frequency and voltage worse than if there was less renewables on the system. And they can often be more variable and uncertain, as I explained earlier. And they also are more spread out in different locations on the system, which impacts on things like voltage. So these increase the complexity of operating the power system. They increase instability and security locally and system-wide, and they increase the need to manage power flows and support the system and increase the requirement to balance the supply and demand. So flexible resources are needed to help meet these increased needs caused by the renewables as well. Finally, we got the network that we're operating with, and we're trying to really enable the transition towards the future power system, and that means enabling demand and renewable generation to connect in a quicker way. And in that, that's very important to enable the decarbonized future power system, so you can have a lot of electrical demand, which is being met by clean energy. That's thinking about the likes of renewable heat as well, coming from the electricity system, renewable and low carbon based business operations as well. So what this can cause issues with then is that there are often constraints in trying to develop the network upgrades in time. These are very big infrastructure projects and might take numbers of years to develop. And so alternative approaches should be considered then to be able to do this quicker, or to defer the need to actually develop the network if it's possible to use just the existing network. So managing congestion through flexible technology or operational approaches then is something that can be considered to prevent the disruption, can continue the connection while also not causing issues on the network. And we also want to use all the renewable energy available in useful ways and not waste it at times when there's too much, and then need other less carbon-friendly resources when there's too little. So trying to do that in a way as well to make sure that we can use renewable energy as much as possible, that's part of what's driving this. So where flexibility comes in then to help with that is that if we have resources that are available to be used to meet the different system needs when they're needed, that can be very useful. Flexibility then also flexible resources should have a speed of response which is fast or slow enough to meet the different needs, in terms of the different timeframes as I outlined it. And they need to be able to meet the need where it is. So is it a system-wide issue? Is it a local issue? They provide the right metrics in terms of meeting a system need. So is it power balance in terms of active power? Is it reactive power in terms of supporting the voltage? Is it inertia? So it's providing the right needs. And then we also have to consider what are the resources that are providing it. Is it generation or demand? Is it network equipment? Or is it an actual change in the operating approach to operating the power system? We need to make sure they're also impactful and compatible with the context of trying to maximize renewables and minimize emissions, and that they're also effective in preventing disruption to the power system, so they are helping meet our system needs. So that's really the drive around flexibility and what flexibility can do to help with managing the power system. So that's maybe a bit relatively theoretical. I think what would be useful now is to go into a few more practical examples of how flexibility can be developed, using some examples from what we have done in the Northern Ireland power system. So a bit of context in terms of the drivers specifically for ourselves. We are on a transition from, in 2020, we had 40% of our electricity being met by renewable sources, and to 2030, we're looking to have 80% of our electricity provided by renewable sources. We have a plan around this to achieve these government policy targets called Shaping Our Electricity Future. So this is EirGrid's plan and what needs to be done to enable that transition. And one important aspect then to achieve this 80% renewable energy target, so you can almost think of this as like the average amount of energy over the course of a year being from renewable sources as 80%. But to enable that, we need to be able to provide at any one single time up to 95% of our energy coming from these renewable resources. And for our instance, that mostly comes from non-synchronous resources, so the likes of wind and solar. We don't really have as much in terms of resources from hydro and other renewable resources. So we need to raise what we call the system non-synchronous penetration limit to 95%. So this is the level of demand which is being met by non-synchronous resources like wind and solar. And as I explained earlier, obviously that drives a lot of extra instability on the system and decreases the availability of flexibility from conventional resources. So we obviously have a very big need for flexibility to help manage that transition. this transition is looking at both from the supply and the demand side. So on the supply side, we got a big growth in offshore wind, onshore wind and solar, small scale solar, also some growth in conventional generation as well. On the demand side, we have a large growth in large energy users, especially data centers, electric vehicles and heat pumps in terms of trying to decarbonize transport and heat, and also general social and economic growth, which is causing a big raise in our demand at the same time as we're trying to transition our supply. So, and this is obviously driving many of the drivers for flexibility that I explained earlier. So we're decreasing the availability from conventional sources, increasing the need for flexibility by bringing on more non-synchronous renewable sources. And we want to maximize the use of the network for efficiency point of view and to make the transition as quick as possible. So how we look at that in our Shaping Our Electricity Future plan then is we need to look at changing how we develop the networks, how we operate the system, how the markets operate, and then our engagement with different stakeholders to enable all of that. And so what this looks like in terms of a transition over time. So this will be a gradual thing over time. So we need to be able to manage how the power system is different in different years. So in general, the amount of conventional generation will decrease over time. The amount of services and energy we're getting from renewables, from demand flexibility, storage, low carbon inertia services, and others will increase over time. And at the same time, we're increasing our SNSP limit. Currently, we're at 75%. So that means we can have up to 75% of our demand met by wind and solar at any one time. And we need to increase that to 95% over the course of the decade. So there's a need to be able to identify what's needed, incentivize them then, especially in terms of markets, and then have that capability arrive to be able to operate the system at these levels to achieve the 80% renewables targets. So some examples of what we're doing then to achieve this, if we start off with that kind of incentivizing aspect of it. So these are where markets come in. We're trying to incentivize investment and performance, providing services in different ways that meet the needs that you're trying to achieve and increase the amount of flexibility available. So there's multiple different aspects of markets, but one that's very tangible, which I'll focus on here, is system services markets. So this is where we've looked at creating services for each of the various different system needs that I explained earlier in terms of having inertial response as a specific service that we can pay for and incentivize people to provide that service in ways that are useful to us. In operating high renewable power system penetration. Reserves then also in terms of maintaining that frequency stability, ramping in terms of looking at that longer term aspect of uncertainty and variability over 1 hour, 3 hour and 8 hour horizons. So we felt that that was important to be able to incentivize services to be able to meet that level of uncertainty and variability. And also then voltage regulation in terms of reactive power to help support the voltage as well. And within those products that we developed, we created aspects that would incentivize the performance of providing those services in ways which are useful to the operation of a power system with high levels of renewables. So for example, with inertia, we incentivize provision with lower minimum generation levels. So a practical example of that, there could be a combined cycle gas turbine, so a large gas plant who's providing that inertial response. And normally they need to be on at a minimum megawatt level, let's just say 200 megawatts if they're a 400 megawatt generator. And through this service, we would incentivize them that if you actually provided that with 100 megawatts rather than 200 megawatts of generation, then you'd get paid more for this service. And what that means then is an extra 100 megawatts becomes available to renewables to provide on the power system instead of being taken up by the gas generation. So that's a way of trying to incentivize additional flexibility. So there's flexibility in being able to operate in this different way than would be the norm. And also then in our fast frequency reserve, we did something similar for voltage regulation product. And then we also incentivize faster response times down to 150 milliseconds in our fast frequency response service. So normally this was a service that would respond within a number of seconds, but then we incentivized response down to the millisecond level, again, trying to get better support for the frequency on the system. So that's again another aspect of how you can incentivize things in markets to get that additional flexibility that you want to help support the power system. Another aspect then is also just in literally the amounts of money that are coming from different parts of the market. So we have put in a lot of work to make sure that the system services are valued more, especially as we're moving to this future power system where the majority of the energy will come from renewables. And so a lot of the value on the power system comes from being able to support that high renewable power system. And so the amount of money available for those kind of services would need to increase as well in comparison to the rest of the market to help enable that incentivization, to help drive the investment in the resources to help provide that those kind of system supporting services. So once you have the markets in place and you're able to incentivize, then the flexible technologies come along. So let's give a few examples of the kind of flexible technologies that we've been looking at in Ireland. So demand side response is one that often comes up and sometimes is the main thing that's being discussed when we're talking about flexibility. So demand side response is involving users of electricity. So this could be businesses, residential, commercial, industrial. They have the capability to change their electricity usage patterns from the normal or current consumption patterns to a different pattern. So they could either temporarily turn down their demand, turn up their demand, or shift demand from one time to another. And normally that's in response to signals. So if it's an explicit signal, such as with a product with us, that we would issue them an instruction to change their output. Or it could be implicit signals, as I explained before, like availability of different time of use tariffs or wholesale electricity market prices, which are different at different times, and responding to that. Some of these demand side response can also provide the kind of fast acting reserves as well, and they can operate in different timeframes from the millisecond up to the longer term kind of ramping aspect. And there is a large focus on demand side response from European and national policy. So there's a network code for demand response being developed at the moment, trying to develop a number of rules to help and legislation to enable growth in demand side response. And then in Ireland, there is a national energy demand strategy and a target to get between 20 and 30% of our demand to be flexible by 2030. So on the right, I just have a simple example of a changing demand profile, where in the dark green is where the normal profile would be. And this has a low level of demand over the nighttime, which might not be that useful if there's a lot of renewables and we have to turn down the renewables because there isn't enough demand. And then over the peak later on in the day, that can be driving the need if there aren't very many renewables available, that we need to turn up non-renewable resources. So then if there are incentives like changing profiles for EV charging based on pricing and things like that, then you can make this profile a lot more flat. So you bring down the peak, which will be more useful for managing over the peak, and you can increase demand over nighttime when there might be the renewables available. So that's an example of what that can look like. Next one then is around storage, and especially in our case around long duration energy storage. So this is technology which is looking to store energy in various forms. It can be chemical, thermal, mechanical, electrochemical, and the resources then are dispatching energy or heat for extended periods of time. So that can range from hours to days to weeks, or even seasonal at some point in the future. It's not maybe something we see as much at the moment, but it's something that we'd be interested in seeing in the future. And so in particular, what this is focused on is storing renewable energy at the times where it's abundant. So in the graph to the right, the example here on day one, there's a high level of renewables on that particular day. So storing it when it's available at that time, and then having it available at a time when there's less availability of renewables, and instead of turning up non-renewable resources, the stored renewable energy is available so there's and that's able to be discharged during that time then. And also many of these resources, if you think of the likes of batteries and things like that, they are also able to provide fast acting frequency response services. So they're kind of optimized to be able to provide shorter and longer term flexibility. Low carbon inertia services then. So these are new sources to provide services like inertia and reactive power that I explained earlier, and they manage local and system-wide needs. So there's multiple different kinds of resources here, but two examples to focus on. So synchronous condensers. So these can provide stability services in a very similar way to generators. So they are literally spinning motors. They have physical mass. They provide that inertia through that spinning motor and reactive power in that way too. But what they do is they actually consume power from the system in order to spin, rather than burning fossil fuels like a gas generator might do. So it provides the same stability, but without burning the fossil fuels to do so. Grid forming technology then is where non-synchronous resources who normally cause the problems on the power system stability, like wind and solar and batteries, they can operate in ways which try to mimic as close as possible the behavior of synchronous generators in providing the inertia and voltage support services. So there's ways that can be developed in the technology as well. Interconnectors then are also a resource which is useful. So if you think of different weather and operating conditions in different areas, there can be, if you connect the different areas, then one area can support the other. So if there's an area which has better conditions on a particular day, they have surplus of renewables, no system concerns, they can transfer power over to another area which has less good conditions, like they have a shortfall of renewables or they're experiencing system issues. So that can be a useful form of flexibility too. And they can often provide other fast-acting services as well. In terms of, so that's in terms of technology. Then we also have flexible operations. So I'll go through a few examples of this quickly. So in terms of hybrid connections, we have, at the moment, if you connect, for example, a wind farm and a battery in a certain area of the grid, you need to be able to potentially meet the maximum output of both of those at the same time. So if it was 50 megawatts, you need 100 megawatts on that part of the network. In the future, it's looking at being able to manage that where you don't need the full 100 megawatts. You could still have it at 50 megawatts, and they just split between the two resources, which ones are providing what proportion of that 50 megawatts. So you don't need to manage the full amount. And that's obviously beneficial then from not having as much network development needed to be able to connect on these important renewable resources and the flexible resources to help support them as well. And another example then we have is in helping the distribution system in managing congestion on its network. So in Ireland, the distribution system operator is developing products and services so that when the demand in a certain area exceeds the station load limit, that they can utilize demand response or storage in order to prevent that from happening. In order for us to be able to do that, we need to change our way of operating so that we can have a coordinated approach to operating between the TSO and the DSO. And we do this through aspects around forecasting bid management, optimization scheduling, activation dispatch, and settlement then. Lastly, in terms of the flexible operations, then we look to change our operating approaches now that we have all this new ability in terms of the flexibility on the system. We need to change how we operate, the kind of standards to which we operate the system, taking into account this new ability, and also enhancing our control center tools where we can analyze, forecast, and prevent the issues in a more accurate way. And because of that, we would be more secure then in knowing we can operate to these high level of renewables with this new technology. And there's a process that we have that we follow to make sure that we can make those kinds of changes. So in summary then, I have a few conclusions to go through. So firstly, started off this presentation saying that flexibility means different things depending on who is using it. When they're mentioning it, what it's intended to be used for, and what's the context of mentioning it. But it can be useful to think of it in an abstract way, where flexibility is a kind of a technology resource or a way of operating which can be used to meet one or many system needs. And it has characteristics which are compatible with the context of the operating conditions. So if you think of high renewable times, low renewable times, and you're generally trying to enable supporting the system in different operating conditions. And the drive for increased flexibility at the moment comes primarily from the goals of decarbonising, increasing renewable generation, and maximising the use of the network to increase the transition to that decarbonised future. There are various different new technologies and ways of operating that can be considered flexible, and how they're developed and enabled needs to be based on a balance of incentivizing through the likes of markets and also standards then in terms of changing how we operate the power system and the policies and standards around that. So there is a lot of work needed to increase flexibility, but it's also important to recognize that there is a lot of value in that work. It enables the transition to a low carbon power system in the most cost efficient way possible, while also maintaining the system security, which is of key, the key kind of aspect of what the transmission system operator is trying to do, is to meet the combination of all these various different needs, and flexibility is very helpful in helping us to do that. So thank you very much, folks, for your time. I'm finished there. So, and back over to you, Alex.
Thanks a lot, Martin. I think you've hit the right balance between introducing us to flexibility and a good level of detail in a quite technical topic. Thanks a lot for that. I understand that we have a diverse group of participants, so this is your time to ask any clarification questions to Martin, anything that you would like him to elaborate more. Just to say that the discussion, the full-scale Q&A, let's say, will follow after Iegor's presentation, but now the floor is back to you, to everyone, to ask any clarification questions to Martin. Feel free to raise your hand or drop your question in the chat. If not, then I will ask Iegor maybe to present. So for this, Martin, yeah, please. Iegor, you can share your presentation, your screen, and here tell us about 24/7 and other demand-driven decarbonization approaches. The floor is yours.
Thanks, Alex. How can you see my screen?
Yes.
All right, and thanks a lot for Martin for great talk, and for EirGrid generally for inviting me to talk in this civil society training series. My name is Iegor Riepin. I'm research scientist in Technical University Berlin. I'm part of Energy System Group here. We do energy system modeling. And I think what brings me here today is a project we have had in 2022 and 23 with Google. The company kickstarted 24/7 CFE movement back in 2020. However, nowadays, 24/7 CFE movement is way more beyond Google and ICT sector in general. But we have researched with them various questions on 24/7 CFE, whether it's on costs or portfolios of renewables needed to achieve the system level effects. And my task for today is to talk you through what is 24/7, to present how do we approach this with mathematical models, and highlight some of research results we have had, which I think might be very interesting for you. And I'm happy to talk afterwards with you on any questions you have about this. The things I will be presenting today is a joint work with Professor Tom Brown, who is head and heart of our research group here in Berlin. All right. Good, to set the scene, there are many companies out there who, when buying energy, they look not only for megawatt hour of energy content out there, but also for renewable or environmental credit behind this energy. There is plenty of companies nowadays, for 100 worldwide, who join this Renewable 100 group, and they pledge to match their electricity demand with clean electricity on an annual basis, meaning that they buy just enough of clean energy to match their demand or their consumption on an annual basis. The way how this happens sort of varies. Some companies buy so-called unbundled certificates, such as guarantees of origin. These things are called unbundled because the megawatt hour energy content and the renewable credit behind it are unbundled. And basically, when you buy GO, you buy just the environmental credit. And some companies recognize limitations about the schemes, which I will talk shortly, and they sign power purchase agreements with renewable generators, and then you have a contract with wind plants out there. So basically you buy and energy and environmental credit together. So great, what's the problem? If we match our demand with green energy on an annual basis, there are plenty of problems, but one, and maybe the most obvious one, is there is certainly a mismatch sometimes between your demand, let's say it's a gray, it's your company demand, and the generation of wind plant here, if you purchase wind plant or solar or what else. And even if the amount of energy in this blue chart equals the amount of energy of consumption in this gray chart, there definitely will be times when your renewable resource might oversupply above your demand or have lack of generation when wind or solar doesn't shine. And in case you have oversupply, it's sort of not a big deal because this excess energy you can store, but store comes at cost. You can also sell back to the grid if it's needed, and at worst is worse, you can curtail. But these hours when you have not enough generation from your assets to cover your demand is sort of more problematic because you have to go to the background grid and buy on the spot market. And at these times, the energy will highly likely have some carbon content, but also come at price. And this mismatch between generation and demand is what's called temporal mismatch problem, is one of several things why covering demand on an annual basis is not leading to full decarbonization of power systems. There are a couple of other problems out there. One is generally referred to additionality. So this means, let's say, if your consumption is in Germany, but the guarantees of origin you are buying coming from Norwegian hydropower plants, which were there before your procurement strategy is there now and will be there afterwards, it's hard to claim that your procurement strategy of your company drives decarbonization or does any good for the system. But if you build additional wind or solar plants that is built for your procurement, and it's a new asset, you can say that assets are additional and you drive decarbonization of system. And another thing is usually called locational geographical mismatch, which means, say, it's a good example is Iceland. Iceland is very, very clean system with hydro and geothermal. Iceland does sell guarantees of origin to Europe, and Iceland also has 3 aluminum smelters, which consume bulk of consumption of a country. So aluminum smelters claim that the aluminum is green because it is green. It's produced in Iceland, which is a very clean system. But also these guarantees of origin flow to Europe, and it creates this called double marketing problem. And yeah, there is a number of things. And because of this problem, there is a movement from some companies just to do things right. And the movement called 24/7 CFE, and generally it means that every kilowatt hour of electricity consumption is met with carbon-free electricity sources around the clock. But not only 24/7 is important, but also it's important that these companies in this movement try to work on additionality, so ensure that they procure new assets, and also work on geographical matching. So at least you buy the assets for your procurement, which is located in the same bidding zone where your demand is. Good. The companies who follow this 24/7 CFE matching approach and also general society, there are many things you can ask. What does this 24/7 CFE mean? Some questions you can ask: how do we ensure which portfolio we need to buy, and how do we match exactly demand with consumption, what amount of storage you need? You can also ask a question, how much we really decarbonize the background systems if some companies follow this 24/7 CFE approach. And you can ask various questions, how exactly demand flexibility can help, in which forms, and what is the impact of demand flexibility. One way to approach this problem is with the help of mathematical models. And here I bring some just general presentation of mathematical models as the groups like we are working. What you see here is a power system representation of European power system. Basically, if I summarize very quick what we are doing, we collect an immense amount of data about energy systems out there, and we put it into computer models. And the data which here, at least for power system, we need to collect is obviously the transmission infrastructure. We need to scrap all high voltage lines above 220 kV and beyond. We need to have information about all existing power plant assets out there in Europe, with their locations, their type, their efficiencies. We need to know many more things. And when you collect all this information and you create, sometimes people call it digital twin, even though I don't like this term. So when you create a computer model of energy system, it becomes firstly exciting, and second, it becomes very useful. And it becomes very useful because you can do many things. You can ask what if questions. You can ask questions, what if Germany now reopens nuclear power plants? Or what if we build hydrogen network? Or what if we do something else? And you can give some quantitative insights into these topics. Our group develops and maintains the models and also some open source tools to collect energy related information. We use it as our working horses for our research, but also it's available at free of charge at GitHub and open licenses for anybody to use. There is plenty of research institutions, NGOs, private sector companies who are using it for their needs. And if it's something you are interested, feel free to go and explore and use it if you find it useful. All right. For this 24/7 project, we sort of did the same. We asked the question, what if some company is located somewhere in Europe? We selected some countries like Germany, Ireland, Denmark, follow 20% CFE. And if they follow 20% CFE, what means they, instead of buying electricity for background grid, they can sign power purchase agreements with renewable assets and storage located in their bidding zone, such as to achieve a certain procurement strategy, which could be covering their demand on an annual basis or going really at 20% CFE. And we asked many questions. What is the impact on the system? At what price it can come? And what else? Here's just one cherry-picked results of our project. What you see here is a scenario where some companies are located in Germany in the year 2025. And the chart shows the attributed average emissions of an energy consumption. So this reference case bar above 240 gram CO2 per kilowatt hour shows what would happen if companies have no special policies, just buy electricity on the spot market. And this bar represents just the emission intensity of background grid in Germany. I checked yesterday. Yesterday, the value was 300 gram CO2 per kilowatt hour in Germany, but this is in modeled year 2025 and also annual average. So the value roughly doesn't make sense. And now the bar on the left, 100% RES, means if companies sign enough PPAs to cover their demand on annual basis, they significantly reduce their emission intensity or their consumption. But there are hours, obviously, as I showed in previous charts, that when your portfolio, neither wind nor solar cover your demand, so you have to come back to the spot market and buy some energy out there, and your emission density falls significantly to 70 kilograms CO2 per hour. And then what you see on the other bars is what happens if you follow 24/7 CFE. So 100% here means that you match demand, your consumption with clean energy every kilowatt hour, every hour all around the year. So 100% matching. And by definition, you have no emission intensity in your consumption anymore, at least no scope 2 emissions. And this 98% would mean that you, on average, 98% of time achieve this target. And there are just 2% hours in the year when you cannot cover your demand, and so you still go and buy from the background grid. All right. What else we can do? We can ask the question, how much of additional renewable generation and storage we need to buy to achieve this goal? And we simulate the required procurement, and the exactly shares of wind, solar, and battery really does depend on which country you are. Some countries are much more windy, some countries require more storage, But in Germany, results as follows. So if it's around 4 gigawatt load, here it's 10% of commercial industry consumption in the country, follows annual matching, then you need roughly 28 gigawatt of onshore wind and solar. And in order to achieve 24/7, you need to procure much, much more, as you see in the bars to the right. And the reason behind this is that the really difficulty behind 24/7, there will be a period, maybe a week, maybe more, of doing floating. So this just periods of there is no wind, no solar, an extended amount of time, and you need to really assemble a large portfolio of generators and storage in order to achieve this. If we know the required procurement, what we can also ask the question is how much does it cost? The way how we do it is just we collect all capex and opex of all procured assets. We get a euro term that needed to achieve 27, and then this euro term we divide by megawatt hours of consumption, and we get euro per megawatt metric, which represents just the cost of achieving 27. And this euro per megawatt hour metric is very valuable because what you can do, you can compare this 24/7 cost to annual matching cost, and also you can compare to the average price you pay if you buy energy from the background grid. And the general story in all these calculations is that you can achieve a pretty good decarbonization results with 98–95% of hourly matching with just little premium above annual matching. And then if you just want to squeeze the very, very last grams of CO2, you have to pay quite a lot. But by no means this should, I would like to say that 24/7 CFE 100% is prohibitive because of cost, but rather is the fact that if you just use mature technologies like wind and solar and battery storage, it's just maybe not the right mix of technologies to get to 100% decarbonization. What you do need here, you need some advanced storage technologies. It can be clean film generators, or it can be the long-term energy storage, as Martin presented. But here I modeled hydrogen storage, which means we take electricity, with electrolyzer produce hydrogen, we store hydrogen here underground in salt caverns, and then with the help of fuel cells, we convert it back to electricity. But this is not exactly the one route which you may follow. This route depends on salt caverns, so hydrogen infrastructure there. There are many other forms of long duration energy storages that companies can buy. For example, there is a Form Energy, American company that develops a long duration energy storage called Iron Air, where basically it's reversible rusting of iron, and you can store energy by doing this, and they ship such cells, car size roughly, and this does not require any hydrogen infrastructure. The general story here is that if these companies cooperate with long duration energy storage operators, they can significantly reduce the cost for hourly matching. Here the cost fall by 50%. So the 100% 20% CFE is achieved by roughly 110 euro per megawatt hour, but it really depends on the cost of storage. All right. Another thing which I would like to talk with you today is what is the role of demand flexibility that can play for 24/7 CFE. Many companies who would like to participate in 24/7 CFE have some form of demand flexibility, which can be peak clipping, and some manufacturing can maybe shift their production in time a little bit. Clearly, electric vehicles is a good example, but there is some subset of consumers like big data centers that have another dimension to this flexibility, and that is they can shift some computing jobs and associated power loads both in time, so it means that it can delay some computation in time, but they can also shift jobs in space. And as far as I know, many big ICT companies working on implementing these things. So Google published a couple of blog posts and position papers explaining how the data centers can work harder when the sun and shine blows, meaning shifting things in time, and also how they can produce where they can compute more where there is more clean energy available. What we have done, we have explored a lot how exactly you can use the space-time flexibility to achieve 20% CFE matching. But even though I will now present some results for a data center because I think it's exciting, our work was not just on data centers. We also explored how you can use flexibility on if you have some manufacturing or industrial consumption where you have flexibility in time. It's all available in our reports. But I think this data center story is very exciting because we often hear now about AI. AI is taking over our lives with ChatGPT and things like this. But also, if you think through the mind of energy researcher, what you always hear is that the data centers require a lot of power, and there is a lot of discussions nowadays in energy circles. How do we supply this increasing demand of data centers with some electricity, let alone clean electricity? And the largest data center in Germany now is 170 megawatts around Frankfurt am Main. So it's very, very large. The consumption is like one city consumption, but the modern data centers can be immense. Microsoft is looking where to put 5 gigawatt data center in USA, and 5 gigawatt is just consumption of country of Scotland. So it's a very, very large things. But so if you think through these terms, you think about the challenge. But there is other way you can look at it. You can look at it as an opportunity, because you think, well, if we have a very, very, very large electricity consumers located in our system, like in Europe, and they have some form of space-time flexibility, and we can facilitate this incredible engineering teams of these companies, but also with legislation, with some TSOs, we can facilitate this flexibility. You can look at this as an opportunity to save costs, save emissions, reduce congestions, and things like this. All right. So the third experiment which I suggest for today is let's think we have a European renewable-based power system, and we have, let's say, some geographically distributed data centers out there with some form of flexibility. The question is here, what features of renewable-based system you would look at, such as you can utilize your flexibility? And one feature displayed in this chart is the quality of local renewable resources. What you see on the left is average capacity factors for wind, and on the right for solar. And this basically says that some places in Europe, like North Sea and UK and Ireland, is windier than the rest, and some obviously places in Europe is sunnier than the rest. Well, you don't need to be a research scientist to say that Spain is more sunny than Denmark, but you better call a research scientist if you want to know by how much exactly. And what we have done in this study, we were placing data centers in very, very different places around Europe, and we were asking the question, how do you coordinate procurement of additional renewable resources and flexibility such as to achieve 27 CFE at lower cost possible? And here is just an example of spatial shifts for a system with 3 data centers in Portugal, Denmark, and Germany. And this is a time series of shifts for data center in Denmark. And this is optimized spatial shifts. And if basically it's red, it means Danish data center sends jobs away. And if it's blue, Danish data center takes jobs. And this has a clear seasonal and daily pattern, such as if you face system like this, it's a company will fare and society will fare to use the best resources possible where they are. So basically, here Danish data centers, on average, during summer would send jobs to Portugal or hotels and takes jobs during winter where the winter resources are good. We have done a lot of calculations to ask questions. How exactly? Okay, thanks, Alexandros. I see 10 minutes is enough. We ask questions. So how much a unit for flexibility can save you a unit of procurement, of unit of cost to achieve 24/7 CFE? And the general message here is that, yes, if we coordinate flexibility and 24/7 CFE procurement of additional resources, we can save a lot of costs. So in other words, demand flexibility facilitates efficiency, resource efficiency, you need less procurement, and affordability of 20% CFE. The second very cool things about this is that, well, what we can do, we can take the weather data sets about Europe, and we can take one representative reference as a wind turbine or PV plant, and we can place it somewhere, and we can calculate time series of generation this wind turbine would yield. And we can do this for many, many, many cells, and you can ask a question, how much the generation of wind turbine somewhere correlates with generation of other wind turbines. And this chart shows just correlation follow. And the general story here is that in Europe, you need to move just 300 or 400 kilometers, such as that wind generators generation does not correlate with each other. And this means that you, well, if you have some special flexibility, you can arbitrage on this fact. This can be done with transmission, but transmission power lines comes at cost. You need time to build it. There is not in my backyard, social acceptance, planning, a lot of things. But the data can be moved quicker or cheaper than transmission. There is not back of my yard problem. There is clearly no voltage for flow problems. And what we have done, we have just analyzed how much you can save on 20% CFE if you sign generators which are far from each other as a function of distance. And for example, if two data centers are located at around 400 kilometers far from each other, and they sign generators nearby or on site, and they have, let's say, 10% flexibility, just 10% of jobs can be moved in time and space, you can save at around 7-8% on achieving 100% 24/7 CFE, which is quite a lot. All right, and maybe the third interesting or fascinating fact here is that if you look at solar generation does correlate very, very well. So that means, well, if there is solar radiation in Germany, it's quite likely that Spain has it too. But if you take, let's say, a point somewhere here in Athens, and you take a point somewhere in Lisbon, and you take the generation, like the feeding of solar plant, and you take the difference between them, you get a chart like this, which does say that solar spikes in Athens a little bit earlier than in Lisbon, which is a clear fact just because Earth rotates counterclockwise. And what we can imagine a system where the specially distributed data centers would take more jobs just to follow the sun. So when sun feeds more in Athens, you have more populations or more demands, and it goes to Portugal, and maybe it goes to California, and so on. All right, I wrap up my talk here. I didn't know really how to make a takeaway because I don't present one specific paper. I think the one verbal takeaway from my talk can be that 24/7 CFE is the one-side decarbonization approach where companies try to eliminate all emissions from their portfolio and also think about other very important things, such as additionality of their procurement and locational matching. And along the way, they solve a ton of challenges such as procurement, risk-taking, engineering challenges with this flexibility, and so on. Instead of conclusions, I would like to just point you on some resources you might be interested if this topic of 20% CFE or flexibility is relevant. What you see is the 3 links above is just important 20% CFE resources. This European 20% CFE Hub is a central place where companies interested in full decarbonization in their portfolio meet. They have annual meetings, constant reports, and if it's something interest for you, definitely check it out. The Princeton University Zero Lab has done a lot of great work on modeling-based analysis, like we did on 20% CFE, and you should definitely check it if it's relevant. Another thing worth mentioning is that this topic of hourly matching is not just a topic of in electricity world, it's also a topic in hydrogen world. There was recently a European delegated act which regulated what should be green hydrogen, how do we regulate what is called green. And my great colleague Elizabeth Zane wrote a paper about this. There are rumors that the delegated act will be revisited, and then it means this paper is relevant a lot. So if it's something your NGO, your group is interested, please check out the paper. And last but not least, we have a web page where we list all of the reports, papers, podcasts, what else about this work I just presented in videos and CFI. You can find this in this website, and absolutely everything in this project. So all reports, all papers, even this slide deck is reproducible from scratch. So this means all the data, original raw data about power systems, energy models, all the slides can be reproduced on the laptops if you open GitHub repo and you do the instructions which I wrote. So if you are a company interested in building a commercial product or NGO with an interest on some in-house calculations, or a master student interested in these things, feel free to check it out and use and find it useful. All right, Alex, I give the mic to you.
Great, thanks a lot, Igor. I think it's important, yeah, to understand what is happening on the demand side. What are the decarbonization options and approaches that end users are pursuing, and then of course what is the relevance for the electricity grid and how flexibility kicks in the whole process. Thanks a lot for the presentation. Now the floor is to all of you who are participating in this event to ask any questions either to Martin or Iegor. As we said, we would like this to be as interactive as possible. We understand that different levels of knowledge exist among the participants. So feel free to ask from the more basic, let's say, introductory question to a more advanced one. Feel free to take the floor, to raise your hands. Of course, I have some questions on my own, but first the floor is to you. Okay, then I will ask my question and hopefully warm up a bit. The audience, maybe to Martin. You mentioned demand response as a key aspect of flexibility. So could you name some examples that Ireland is using on that front, on demand response already, or maybe some future developments on that front?
For sure. So think you can kind of think of things that are within the more explicit signals that I was saying about earlier. So what the system operator is doing more directly, and then things which are implicit signals. So explicit, we have market participants who offer demand response. They're called demand side units, where they have an aggregation of a number of demand sites, and when they're instructed by the system operator, they can reduce the demand on those among the aggregation of sites that they have available to them, and so that's quite useful. They can also provide fast-acting reserves, many of them as well. And I suppose that's the main aspect that we have available to us right now. We are, in terms of the wholesale electricity markets, growing developing the capability to have units which can turn up demand at different times. So that might be, for example, where we have surplus of renewables at a certain time, and at the moment what we have to do is to curtail the output of those renewables because we don't have enough demand or export capability to allow all of that renewable generation to generate on the system. So instead of curtailing that renewables and having it wasted, we can turn up demand that can use it then in useful ways. So We have an example of that at the moment with an industrial boiler where they normally use gas boilers, but then at certain times they can switch over to electric boilers to create steam for their industrial processes. So that's something we have a kind of trial looking at that, and we look to develop that as an actual full market participating aspect. And then I guess the other side is the implicit side. So there have been developments over the last number of years of going from relatively simple tariffs in the retail market. So having maybe just a flat tariff for all periods of time, or a daytime and nighttime tariff, which at least is moving towards having some bit of flexibility, encouraging people to use power at night instead of during the day and reducing the peaks. But now moving to time of use tariffs, where there can be a higher cost over the peak times where everyone would tend to generate together, and lower prices than at other times, to encourage use in different times of the day where it might coincide better with the not having so much coincident power at the same time, and where renewables might be more available. So that has been developed over the last number of years, but in the future there is also an intent to develop dynamic pricing, where it's not just changing prices over the course of a day, but what those changes are the same for every day. You could actually have it matched up with what the wholesale spot market prices are. So that would reflect a lot more what is the operating conditions on that particular day. If there's a high renewable period, then that price could flow through. And so if that price is then available to consumers, they can see that, and then they can try and shift their power to the times of day where the price is lower and the renewables are higher, and away from periods of time where the prices are higher and the level of renewables is lower. So yeah, there's a lot of different developments being considered in the demand side flexibility.
Good, thanks a lot, Martin. I see that if there are any other questions, I see that Iegor also posted on the chat. Please, Iegor.
Yes, thanks, Alex, and thanks, Martin. I think the thing I wanted to ask Martin is, you mentioned in the talks that there is a special national energy demand strategy, and that by 2030, 20 to 30% of demand should be flexible. But the thing I think is very relevant here is not only how much of the demand can participate in demand response or have some flexibility, but also how big this response can be, how far you can shift on time, and things like this. So I think my question is, where do you see the biggest contributor on demand side here in Ireland? And maybe second very related question, I know that Ireland likes data centers. There are a lot there, and by 2030, a big chunk of Irish demand, power demand, supposed to be data centers. Are there special considerations, special rule regulation, or expectation from data centers to be flexible at certain level?
Yeah, I think it is a very obvious one where you look at combining your questions. The level of response that's could potentially come from data centers could be quite large, because they are such large consumers of power in themselves, and then as a block, so individually each data center is a large consumer, but then as a block they are also very large. And so I think there is an intent to at least in terms of policy, try to move them towards having demand flexibility. Not sure necessarily in terms of legislation, in terms of requiring it, but I think it's more around that incentivizing kind of aspect. And that becomes then interesting when you think of the aspect that you were presenting on, I think around that following the sun and following the wind and these kind of things. Is that a way that is obviously a technical challenge in enabling that, but then is that something which is easier to do than other approaches to demand response, which would more typically come from actually turning off processes or turning on processes? So you'd imagine data centers would typically like a very stable, steady power consumption profile. So if, I suppose, it's looking at that steady consumption profile, but you just shift exactly where it's coming from in a way that matches better with the the operating conditions in terms of where has the wind, where has the solar, then that could be a useful way of achieving that, more so than trying to get them to actually turn off processes and you know, a reduction in their capability. So, and I think then in terms of other aspects that could be very impactful and large, you know, we've got a few hundred megawatts, I think up to between 600 and 800 registered. And then in terms of how much actively participate, more towards kind of 200, 300 megawatts in terms of that demand side unit concept that I talked about. And that typically comes from businesses at the moment. We haven't really unlocked the piece around residential households being able to participate, but that's something that we'd look to develop in the future. So that's a relatively small volume maybe. And if you think as well as a business, the example I always bring up is like a supermarket that has a fridge freezer, and you can instruct them to turn off their fridge freezer for an hour, and it won't affect their, you know, operations too much. They can turn it back on and recover the temperature and not affect their produce, but they can't really respond for much more than that hour, or else it would cause problems in their core business. So in terms of the volume available there, it might be a little bit less. But then when you think of the likes of energy or electrification of industry and heat and those kind of resources, that's where it could be much larger, because if the costs make sense for them to shift from they're normally using gas or something else to shifting to using electric, then that could be a very long-lasting and large impactful amount of demand flexibility. So the electric boiler is the example I have there, where, you know, if you've got hundreds of megawatts of gas boilers making steam for aluminum smelting or something like that, and then you just shift them over to electricity when there's a high amount of renewables for an extended period of time, then that could be multiple hours, hundreds of megawatts of response. So I think industry, it'll be interesting to see how much can be grown from that electrification of industry. And then the data centers, in terms of who are the large providers, there is still a role, I guess, of smaller providers, but it's just in terms of the volume of impact, it might be less, but it's not to devalue that. Then, you know, this is potentially enabling consumers to actually have an active part in the transition to the future power system as well. So while the volume might not be large, the actually being an active participant in the transition could be valuable in itself. And, you know, a small amount of money to individual businesses and consumers might have a larger impact even than some of those large businesses. So I think there is a bit of a mix that needs to be thought about, the smaller scale and the larger scale.
Good. Thank you both for the question and the answer. Joanna from Zero, I saw you posted a plus sign in the chat. I don't know if this, I should interpret this as like you have a question or not, but please feel free to raise your question if so. And then I have, so Martin, also you good. Martin, you mentioned regulation, and therefore I have like a question to Igor. What is the interplay between regulation and therefore national, let's say, state support and corporate initiatives when it comes to delivering the 24/7 carbon-free energy approach?
All right, I think, well, there are a couple of things to it. One thing is that there is recently a big piece of European legislation called European Corporate Sustainability Reporting Requirements. It came, you know, it came into force in 2023. I think first year they have to report in 2024. And simply put, it requires companies of certain size, above 250 people or so, or a certain amount of net budget, to report on their sustainability metrics. And it includes their allocational emissions, their contractual emissions, and various things. So I think here that everything which goes into more transparent, more granular reporting from companies is for good. Another thing which is often comes in discussion when we present this topic on 24/7, and here it's a voluntary commitment by private companies to decarbonize their emission fully. The question often comes whether should it not be state that supports renewables or advanced technologies? Should we really rely on companies? And here's like the way how you think about twofold. In one sense, yes, the state can do it, and we have example with German feed-in tariff that supported solar and wind takeover and learning curves in 2004 to 2015 roughly. But we also see examples when state support is limited or can abruptly change. Germany cancelled E-Auto Primi at some point. We have seen example in Spain when Spain finished their renewable support program abruptly, and there is a lot of court processes by corporate against the Spanish state because of this. And so everything we have seen in recent years with energy crisis just says that fiscal budgets are tight. We are not always can rely on state doing it. And in either words, there can be a public support and a corporate effort together going along and doing their contributions to move us there to eventually 20% CFE world.
Good, thanks a lot. I'm aware also of the time, but I do have a short question. Sorry, Mara. I would like a very short answer because we talked a lot about flexibility from a TSO perspective, from an end user perspective. What if we don't have flexibility? And maybe a short answer. What if we don't have flexibility? What would be the consequence either for the energy system or for end user decarbonization approaches? Martin, maybe you would like to start, and then Iegor, and then if no other question, we can actually wrap up the webinar.
Yeah, I think the short answer is you wouldn't, from a TSO perspective, we wouldn't be able to operate the power system with the high levels of renewables. We might have a lot of them connecting onto the system, but then in terms of enabling that in any given moment in time, when I was presenting earlier, I was saying up to 95% of power coming from wind and solar, we wouldn't be able to achieve that. We would need to operate at lower levels in any given period while keeping the system stable, because if other flexible resources don't come in to help keep the system stable in ways that coincide, that are useful to enabling renewable electricity generation, then we would have to basically curtail the amount of renewable energy that can be generated on the system. So that's obviously an overall negative impact then from the power system decarbonization perspective. So it would mean either wasted renewable electricity, and that has a knock-on impact of then will the investment in the renewable energy come at all if a lot of it is going to be wasted. So it's important for us to be able to operate the power system flexibly to enable operating up at those high levels of renewables.
Thanks, Martin. So indeed, very much needed. And Iegor, from your perspective and the 24/7.
Well, I once asked ChatGPT, hey ChatGPT, we would like to build European system, clean, sustainable, reliable, robust. What should we do? After all, it's my sort of lifelong question as research scientist, and it's good to ask the wisdom. And ChatGPT said me suddenly, well, we should just build 600 nuclear power plants in Europe, and the things is done. And well, if we don't have flexibility, we will go to some strange solutions, which either comes at huge cost, or which brings us to very, very hot climate situations. So we better work on flexibility.
Good, and with this optimism, thanks a lot, Iegor, and thanks a lot, everyone. I don't know if you have any questions in the room. If not, then I would like to thank both our experts, Iegor and Martin, for your time and your inputs. I understand that it's quite technical topics, but I think we managed to build some knowledge among the group. If you have any questions, then feel free to reach out to us or to the experts. And please do not miss our next webinar. So it's the last webinar of the three-part series. It is going to take place on the 13th of December. It's called Connecting Consumers. And RGI invited again two experts in order to discuss energy metering and pricing and what is happening at the moment and what are future trends. Thank you all for your attention. Thanks a lot, Martin. Thanks a lot, Iegor. Thanks a lot, Mara, for the support. Feel free to be in touch, and we can take it from there. Thanks a lot, everyone. Have a nice Friday and have a nice weekend. And all good. Thank you.